welcome from my side to you on your screens worldwide. I'm quite happy that so many of you made it to this webinar, which has a very interesting topic, I think, because we have a lot of discussions with our customers between the benefits of highly accelerated live testing and accelerated live testing, and this was the main motivation for doing this seminar. Before I introduce my details, I would like to show you hello. And like this, I will show you the outline. I will start with a short introduction of myself, my company, and the motivation for this talk. Then I will give a short overview about qualitative and quantitative reliability tests, before we then getting a more deep dive into the topic of highly accelerated live tests and accelerated live tests, where we're gonna discuss key factors in planning these tests, purposes of these tests, and I will also show you some examples for an HALT and an accelerated live test. After this deep dive, I will then make a short comparison between HALT and ALT tests before I come to the summary of this webinar. But let's start with an introduction of myself. My name is Ken Lukan, and as Alex already told you, I am the deputy head of the reliability department at the Institute of Machine Components at the University of Stuttgart. I came to Stuttgart already in my diploma studies. I studied mechanical engineering, and already in the studies I learned about my favor about reliability engineering. So I decided to start as a PhD student at the reliability department of EMA. And here my big topic was all about representative load spectra. So I'm currently doing my PhD development for methodology of load spectra. Motivation for this was industry working group, where I was the project leader. In the industry working group, there were 10 European commercial vehicle industry participants working together to determine standard load spectra for the commercial vehicle grade. So this was a very interesting experience. I'm also part of the maintenance team of the IEC standard 62506, so the standard product accelerated testing. And last but not least, I'm also a founder and a consultant of the tech transfer company RelTest Solutions. What is RelTest Solutions? RelTest Solutions is a 100% Institute of Machine Components. And here on the left side, you can see the three founders of RelTest Solutions. It's Martin, Alex, and myself. Here you can see where we started to handle stuff in reliability engineering when we started our PhD at the Institute of Machine Components. And already in 2017, we started our first consulting industry partners. Within 2017, we recognized the raising request for support in reliability engineering topics from the industry. So we decided we have to establish solutions to transfer our reliability knowledge, our latest research results from the university to the industry. That means we have a long-term cooperation with the University of Stuttgart, and we also have a long-term cooperation with the company HALT and ALT. We are collaborating with them in the topics of reliability seminars and in the exchange of reliability expertise. As you can see, we have 3 different types of reliability seminars. We are doing a reliability basic seminar, a design of experiment seminar, and a specific electronics reliability. And that this company was needed are showing the number of our customers so far. In 3 years, we already had more than 20 customers, and we supported them in reliability topics throughout the whole product life cycle, starting within the planning of the product and ending within the recycling. So far, we did projects defining reliability and maintainability targets. We did projects according how to use prior knowledge, especially in combination with reliability test planning. How can we use prior knowledge to plan reliability tests? But we also did a project where we defined design weakness and of course we also had projects in field data collection and also in field data analysis, which is my favorite field of interest, representative load spectra, which are quite important also for the next product generation, beginning in the reliability targets. But that should be enough from our technology transfer company. Let's have a look at the motivation for this webinar. When we are talking with customers, most of our customers, they know different kind of reliability tests, like you can see them here on the left side. Degradation tests, burn-in tests, but also the highly accelerated life test as well as the accelerated life. And when we are doing reliability tests, it's quite important what kind of purpose should the test have. Do we want to improve the reliability? Do we want to measure the reliability? Or is it a total other purpose of the test? And with this webinar, I will try to answer, especially for HALT and ALT, the answer for what these tests can be used. But let's start with an overview about reliability tests in general. When it comes to product testing and the product development, we are doing a lot of different tests, as you can see the types on the right side of the top. We are doing functional testing, we are doing environmental testing, we are doing verification testing, and in the end, hopefully we are doing also something like reliability testing. And reliability testing is some kind of special, because reliability testing contains aspects of course, of the verification, because in reliability you want to measure probability. It contains also part of the functional and of the environmental aspects. So this is quite important that we are considering these aspects too, and we have a look at them over time. General purposes of the reliability testing then are, of course, we want to measure and to demonstrate the reliability of our products. Therefore, in most of the cases, we have to determine a vital distribution, we have to determine effects on the reliability. Second, quite important purpose of reliability testing, especially when we have a look at the early product development phase, is the improvement of the reliability. And here it's quite important that we get knowledge about our product to learn what are the critical failure modes, what are their root causes, and are they relevant for the future. But let's have a look at quantitative reliability. Their purpose is quite clear. We want to measure the reliability, and the failure root cause here is the robustness and the design. It's not necessarily a lack of robustness, but we want to measure the lifetime, the robustness and the design. We want to do this based on representative field loads because we want to have a good prediction for our reliability in the field later on. Typical test types here are the end-of-life test, the accelerated life test, the reliability demonstration test, and degradation test, which I show you quite quickly here. In a degradation test, we measure over the time our degradation characteristic, then we are estimating our degradation model. We are done making a prognosis and when the end-of-life criterion is reached, and then we can make a classical vital analysis to measure the reliability of our product and, for example, to demonstrate the reliability requirement. So demonstrating a reliability requirement is a classical purpose of a quantitative reliability test. On the other hand, qualitative reliability tests, they have quite clear the purpose to improve the reliability. And therefore, their root cause is more design weakness and production error. And here, any kind of load which is suitable to identify this design weakness or the production error is reasonable to test. Typical test types here, of course, starting with the highly accelerated life test, the highly accelerated stress screening, the highly accelerated stress audit, environmental stress screening, and so on. But the purpose here is to improve the reliability. And let's have a look at this in an example of the bathtub curve. Let's assume we have this kind of product. We haven't measured it, but if we would have measured our failure rate, then this would be the result. Okay, when we are now doing highly accelerated life tests, we are identifying our design weakness. If we are doing HAS, ESS, or burn-in tests, we are reducing production errors. So this helps us to shift the bathtub curve down to reduce especially the early failures and to improve the reliability. And therefore, also the main focus of qualitative tests are the early failures. So we want to improve the reliability and want to fix these kind of failures. This brings me to the first topic, the highly accelerated life test. We first get the deep dive in. Purpose, as mentioned before, for the highly accelerated life test, quite clear. We want to improve the reliability, and here we have the detailed purpose. We want to identify our failure modes and design weakness. And there's a very, very big benefit of highly accelerated life tests because they only need a short test time, short test duration, and a small sample size. But therefore, on the other hand, we have to go that high with our stress that we reach the production limit. And this can be critical because going that high with our stress level, we have to think about, is this failure we are seeing in a highly accelerated life test relevant for field load condition or not? So a failure analysis is necessary. And therefore, the highly accelerated life test can be described more than a process called test-based test. Starting with the test itself, then we are seeing some failures, and we have to analyze if the failures are relevant for the field load condition. After that, we can improve the design if it's relevant for the field load condition, and then we have to validate our design improvement. We are repeating this process until we do no longer see any kind of relevant field load in our product. What is necessary to plan such a highly accelerated life test? Most beneficial and necessary is product knowledge. For planning such a test, you need the product designers on board. They can help you in the area of stress definition. So what kind of stress types do we use? What kind of stress severity do we use? After that, then we will have our process with the test execution, the failure analysis, then we are making a decision, is the improvement necessary or not? And if yes, then we improve the design and make it loop back to the test execution. Key factors for planning such a highly accelerated live test is, of course, the stress type definition, the stress severity definition, and failure analysis and design improvement, because we don't want to fix the wrong failure modes, because this will lead to oversizing in our work. Let's have a look at the stress type definition. Typically, stresses applied in highly accelerated live tests are mentioned here in the IEC 62506. It's typically temperature, vibration, shock, and so on. But of course, I mentioned it before, a highly accelerated live test is not limited to the stress. Here it's only important that the stresses we are applying in our tests are triggering the relevant failure modes, or the early failure modes, or in general the failure modes. Here it's the best strategy to make an FTA or an FMEA to identify the stress types which are triggering most of the potential failure modes. And this would be the best base to start a highly accelerated test. Let's talk about the stress severity definition. I've told you before, the stress goes up to the destruction limit in a highly accelerated live test, and we're doing this by stepwise increase. But here it is quite important that we also define a maximum stress level. And I will show you in the example of the Wheeler curve why this is so important. Let's assume your product designer used a material where this Wheeler curve is representative for, and you have now to plan a highly accelerated live test, and you start with a very high stress level, like for example here in the area of low cycle fatigue, and of course you will see quite soon a failure within this area. Yeah, you can say, oh, quite good, the test was finished quite fast. But on the other hand, imagine, what have you learned from this test? And you haven't learned a lot from this test, because you just validated the Wheeler curve the product designers used to design a product. And therefore, it's beneficial to set the maximum stress level under the stress level and planning then our step stress until this maximum stress level, because only then we will gain new information about our product. Also, very important for the highly accelerated live test is the failure analysis and the design improvement, because fixing failure modes may also lead to oversizing in our product. So we have to make sure that the failure modes we are going to fix are also relevant for our field load condition. And therefore we have to make an evaluation of the failure mode, starting with the root cause analysis. In the root cause failure analysis, we have to identify where the failure in our system is happening, in our subsystem, on the component level, and what is the root cause for the failure and which stresses may cause this failure mechanism. After that, we can have a look and compare the stresses causing the root cause with the stresses our products see in the field, like for example, mechanical influences, mechanical active substances, contamination, and so on. Is the stress type relevant for the field condition? Then we should think about in the next step, is the stress level reasonable? And here we have to consider the operating margin of our program. Within these, a margin between the lower operating limit and the upper operating limit, our product is operating. And if we see failures within these margins, then it's reasonable to fix them. When we go now more to the right or more to the left, then we will reach our upper and lower destruction limit, which is in this example quite reasonable. Here I would say this is quite okay, because we have a good distance between our operating margin and the destruction limit. But imagine if we have no failures in the upper destruction limit, we are going to fix these failures, we are improve our design and shifting the distribution of the upper destruction limit more to the right, then we are on the best way to over-design the product. And this has to be prevented. This brings me to an example about the highly X-rated life test. DC-DC converter for airplanes, which is listed in the IEC 62526. Here, three kinds of highly X-rated life tests were performed, starting with a low temperature test, where they recognize that the startup is quite unstable. They identified possible root causes, but in the end, they came to the decision that this is not necessary to make an improvement, to make a design improvement, because we are here already at the limit of our technology, and we more have to be ensured that the DC-DC converter is operated within the limit of technology. And the next highly X-rated life test at high temperature, the 12-volt voltage disappeared. Reason for this was that there was an internal temperature limit which causes the shutdown. And this is a typical kind of failure when you're getting a potential or a reasonable failed part back from the field, which is running in your test. So here we have a typical kind of a random failure, because if the limit is too low, then the software will shut down the DC-DC converter. The customer will think, okay, it's failed, and therefore the company here did the action to adjust the limit which was defined in the software. Another highly X-rated life test was performed for the low tide vibration. Here they remarked loose screws and unstable voltage. Typical process problems were here because we had screws which were too loose, and we have some hand solders which were failed. So in this case, the company applied Loctite to prevent the loose screw, and they optimized their solder process to optimize the solders. As you can see here in this example, the highly X-rated life test is a quite efficient tool to identify typical random failures of the product or also early failures. And this is the biggest benefit we will get when applying highly X-rated life. This brings us now to the topic of X-rated life tests. And because highly X-rated life tests are used to improve the reliability, it's quite clear we now have a test which is here to measure the reliability. In detail, with an X-rated life test, we can determine and describe the relationship between the stress and the lifetime of our product. And with this knowledge, we can then make a prognosis for the reliability of our product field load condition, which is quite beneficial because an X-rated life test is finished much, much faster than an end-of-life test on representative field stress condition. Typical process of planning an ALT starts, of course, we have to demonstrate the reliability requirement. And with this requirement, we go into our planning. We have to define our test levels. We have to define the sample size per test levels. And after that, we have to execute the test. And then a very important step is necessary. We have to make sure that on all test levels the same failure mechanism. Of course, the same failure mechanism, especially as it will occur in the field. This is very important because we want to make a prognosis for the field condition. Therefore, we have to make sure we see the same failure mechanism. If we have the same failure mechanism, we can then make a prognosis for the field reliability. Key factors here for planning are the number of test levels which are necessary, the location of the test levels, so the stress severity, how many units per test level, and as I mentioned it before, we have to make sure that we see the same failure mechanism on all test levels. Let's start with the key factor, how many test levels are necessary. And of course, the answer here depends on the lifetime model, which suits best for your product to describe the relationship between stress and lifetime. If we have a linear relationship, then test level x1 and x2 would be sufficient for an accelerated life test. If we are not sure if we have nonlinearity within the lifetime model, then we should add a third test level to check this. So in the end, if you are not sure if you have a nonlinearity in your lifetime model of the product, then make it safe and test the third level too. Let's come to the specification of the stress level, starting with the highest stress level, which we call here stress level 1. For the stress level 1, it's quite obvious that we have the biggest benefit of an accelerated life test if the test duration is as short as possible, and therefore we want to define the stress level as high as possible. But we should not go above the technical maximum of the acceleration limit. And in this case, this means the limit where we do not longer see the failure mode, which is relevant for the field. So if we have a changing failure mechanism, like going up with the stress too high, then we should getting back and down a little bit that we see the same failure mechanism like in the field. Here, of course, the results of a highly accelerated life test we maybe have performed in advance of this test may help us in planning the highest test stress level. Let's have a look at the lowest test stress level, the stress level which is quite unique to the field stress. Here, of course, it's quite beneficial on one hand to have this quite near to our field stress level, because then we have a high prediction quality, but on the other hand, we also have a very high test duration. So two goals which we have to deal with in our compromise. On the other hand, if we define the stress level too high, we will have a very huge scattering in our field level prognosis. And in the end, here you have to find a compromise between precisement of your reliability prognosis for the field and your test duration. And typically, here the boundary condition in your test levels are always giving you the opportunities you have for planning the accelerated life test level 2. Third key factor for planning an accelerated life test was the number of sample size per test stress level. And here it's always the case that at the highest level you have to test fewer units than on the lower level. Reason here is if we test more on the lower level, of course, we are raising our prediction quality for the field level condition. There's also a formula where you can calculate the proportion of the parts which have to be tested at test level 2 based on the extrapolation factor for what the input of the test stress level 1, 2, and the field stress level is necessary. And based on this relationship, the proportion of the parts which have to be tested in test level 2 can be calculated. It's a formula from the master of accelerated life testing, Nelson. This brings me to the example of the accelerated life test. Here, as announced in the beginning, the example for the commercial vehicle brakes and for the air brake. If you are interested in this example, you can download the technical recommendation of the working group from our homepage. But now let's have a look together at the example. For this example, it is assumed that 1 million load cycles with the load level of 6 bar correspond to a service life of 2 million kilometers. So 2 million kilometers is a typical lifetime objective for the commercial vehicle industry when it comes to long distance mission. Boundary conditions for the accelerated life test are: we have already defined the test level 1 with 16 bar. The reason here is this was the maximum of the air pressure cylinder. Then test level 2 was defined at 9 bar, and the field level I've read it before, 6 bar. We have to prove a reliability requirement of 90% at 6 bar with a confidence limit of 95%. Here you can see the listed test results. And first step now is we have to check if we see the same failure mechanism on both testing. And what we can use for this check, of course, we can compare the vital shape parameters. And in this case, they are quite similar. It's not every time the case that these are so similar, because in a lot of cases, we see lower scattering at our higher load condition, and therefore we see here, we see lower scattering at the higher load condition, and then we will see a higher shape parameter, for example, 60 bar or whatever the highest load condition is. But in this case, we are quite satisfied. We see the same failure mechanism. In this case, it was fatigue failure of the caliper of the brake. Then we are making our prognosis for the field reliability. We estimate a model for 10% percentile because we have the reliability requirement of 90%. We estimate our confidence intervals. Then we have to look at our field level condition, and luckily we see here that the requirement lies on the left side of our 95% confidence. So luckily we succeeded in measuring and demonstrating the requirement in this example. This was a deeper look into highly accelerated life test and accelerated life test. Let's compare these tests more directly. The table you can see here on this slide is of Mr. Young. You can find this table in his book Life Cycle Reliability Engineering, which is a very good summary here for the comparison of highly accelerated life test and accelerated life test. And therefore I will only discuss 3 issues of this table with you. First issue, it's quite clear we have different purposes between highly accelerated life test and accelerated life test. Highly accelerated life test reliability, and in an accelerated life test we measure the reliability. Let's have a look at the severity of the stress. In highly accelerated life test, we discussed before we go up to the destruction limit. And on the other hand, in accelerated life test, we have to make sure that we do not change the failure mechanism if we go too high in our test condition. So Mr. Young prefers here to stay below the operation limit, but of course you can also go upper than the operation limit, but then you have to make sure that you still see the same failure mechanism as in field load condition. This might be very beneficial, especially for products which have to last 30 years or something like this. Last aspect I want to discuss with you is the failure cause. Highly X-rated life tests, they address the design mistakes, the early failures. And X-rated life tests, on the other hand, they are addressing lack of robustness and design. But what does this mean? When do we have to apply them in terms of our product development process? And as you can see here, rough reliability management process starting parallel to the planning phase and the product development, ending at the recycling phase of the product development. The reliability management starts typically with the reliability planning, the weakness analysis and the reliability improvement, the reliability testing and the demonstration, the reliability assurance in production, and in the end, we also want to learn something about the reliability within field, about the loads conditions at our product in field. And of course, HALT are used to improve the reliability. Therefore, they are typically improved here in this phase in the weakness analysis and the reliability improvement. After we have a quite good reliability improved, we do not see longer any kind of early failures, we then can perform an accelerated life test to measure the reliability and to demonstrate the reliability for the condition. So it's quite beneficial to do both of these tests. Let's wrap this webinar up, starting with the highly accelerated life test. They are very effective when it comes to improvement of the reliability. They have a short test duration and small sample size. But on the other hand, we still have to make a failure analysis to identify is the failure type relevant for improvement or not. And another disadvantage is we can't measure the reliability with a highly accelerated live test. Accelerated live tests, on the other hand, they are used to measure the reliability. We are estimating also a lifetime model to describe the relationship between the stress and the lifetime of our product, which can be especially beneficial when we have to make reliability prognosis for different kind of markets where different kind of load conditions are relevant. And an X-rated life test, at least compared to the end of life test, has a quite short test duration. But of course, if we compare it with the highly X-rated life test, then it's quite longer. Another disadvantage is we only want to see wear-out failures in an X-rated life test. So in most of the cases, we're doing an X-rated life test and we have to deal with still with early failures. It's quite probable that we have to redo our X-rated life test after we have fixed these early failures. Of course, estimating a lifetime model is connected with a little bit of effort, so we have a quite big sample size of X-rated life tests. But let's come back to the beginning of the seminar. What test strategy is more beneficial? The answer is quite clear. Both are beneficial. We first have to do the highly accelerated life test in our reliability process to improve the reliability, to prevent early failures. And after that, we can use the accelerated life test to measure and to demonstrate the reliability of our product. And this is the most beneficial way to ensure that we reach the product's quality and reliability we want to have.